Okay. So let me right. So let's continue our summarizing. So yesterday we talked about the normal and moment cost, the stress distribution. They need to add up together, right? So yesterday we have an example like this, and then we transfer this real case into shear moment diagram form. Okay, and the most important things here is that you have a oblique force and act with this small distance. This small distance will cause moment. All right, so you can move the p sine 60 and p cosine 60 to the c, no problem, but you need to add up a cost the moment. Otherwise, this loading will not equal to this one. So if you add up MC, okay, the external moment caused by this force arm, okay, this will equal to this condition, okay? And then after that, we plot V and N, and we found that, and also N here, because N also, we can determine this N by cutting two sections, and you find that the first section has the normal stress, but there's no normal stress or normal force in the second part. And then because you are going to determine T and C makes sigma stress, so you can, because T here is, you can see this is positive, so you can have the and this is positive as well, so no doubt that sigma T will occur in the first section. But the compression has something different, because there's nothing here. There's something for tensile. So this normal stress may cancel the compression due to the moment. So you need to check both this one and that one value, 1116.8 value and 571.2 value, to check if this normal will consume all the moment induced compression stress. 就你要去确认说这个拉应力是否会抵消掉所有的弯举制造的压应力。OK， 那这边就是弯举制造的压应力啊，一个是这个值，一个是这个值。那右边那个值就是没有抵消，左边这是有抵消。哦，所以我们两个都要确认看看，我才知道哪个是对的，哪一个是最大的。All right, so finally, quiz 2 will be held in the next Wednesday. All right, chapter 4 and 5. All right, chapter 4 and 5. Well, you will see, yeah, basically chapter 4 and 5 combined together. Right, and also the most important thing is that the chapter 7 is the biggest, well, material science engineering important chapter, okay? Because you can know the stress distribution or orientation in all the points in the material. Okay, now then yesterday we introduced the stress representation. We also mentioned what is tensor. Tensor called 张量. And this is invented by Einstein, Albert Einstein. Okay, the genius. Okay, this invention is really genius because this allows us to use computer to determine the stress distribution. You can imagine that if you learn the introduction to computer science, 技概, okay, you know that the matrix is actually you can use the index to go through the matrix. The matrix has 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, right? Actually, this 1, 1, 1, 2, 1, 3 is, you can use this index using for loop and to go through all the elements to the matrix. So actually, this sigma, this representation 1, 1, and 2, 2, very suitable for computer calculation. Okay, so this is very nice invention, tensor, and it also can. So that's the reason why you see there was a really old and classical movie called Matrix, 骇客任务, right? So why we call matrix? Because matrix is actually can represent it to everything in the world. 它可以代表世界上所有事情，力学、图像 ，OK， 全部都可以代表。所以这就是为什么这个虚拟世界可以 call matrix。当然也有母体啦，也就是我们在 embedded in the matrix， 当然没有问题。但是有另外一个意思就是说，其实矩阵它是可以，它可以去代表世界上所有的事情。这你看到的世界都可以代表3维、4维、5维、6维的矩阵。虽然我们只能看得到3维，对不对？但是实际上会有更高维的空间，是我们没办法想象的。但是矩阵就可以做出来，就可以把它，所以这是一个非常厉害的一个发明。当你越来越认识这个世界的时候，你会觉得哇，这 matrix 跟 tensor 实在是一个很有哲理的东西。Okay, right. So let's continue. So sigma is actually the symbol for stress. Okay, and X means XX. All right, and which means that this is a normal stress because your plan has the normal vector parallel to your direction. Okay, so suppose this stress is normal stress. For shear stress, tau xy, actually you can use sigma 12 in tensor form, right? This is tensor as well. Sigma 1, 2. So you can see that this is a shear. Okay, next we talk about plane stress. Plane stress is that the stress is only on the XY plane. So there are only 2D we talk about here. There's no stress on Z axis. So your stress has anything has 3. Anything 1, 3, 2, 3, 3, 2, anywhere. If you have the sigma 3 something, we don't discuss this. All right? So it's called plane stress, 平面应力. So you see, you don't have tau xz. You don't have that, right? You don't have tau yz. You don't have that. You also doesn't have this surface, is sigma zz. You don't have that, right? You don't have z tau z y. You don't have that because if you have z on it, we don't discuss this. So all we left, we only have 8 things: sigma s tau xy, sigma y tau yx, sigma x tau xy, sigma y tau yx. That's it. Okay. So that's called stress, plane stress, 平面应力. So now this is the norm sigma y. Okay, this is norm. So we know that sigma x, tau xy, sigma y, and then we want to get the stress component sigma x1, new axis x1, tau x1, y1, new x1, y1. Okay, so this is a new axis, and we want to know sigma x1, tau x1, y1 component. Again, we talk about the same stress element. So the stress state is the same, no matter how you change your coordinate. All right. So what is the sigma x1, tau x1, y1 component on this? So stress on incline, continue. Okay, the stress diagram, if we put that in a more oblique. Okay, so here, this is how x1, y1, x1, y1, right? And this is sigma x1, okay? And this is tau yx, sigma y, and this is tau xy, and this is sigma x. Again, they are known, okay, and they are unknown. All right, the pink one is unknown. Okay, so again, sorry, I need to get the incline, right? Incline. So we just cut it from the upper left edge, and we cut the theta along the angle. All right, so we cut it and we leave this small triangle. Maybe it's a cake shape. So this cake shape has tau x1, y1, sigma x1 as a new coordinate and new composition, new component, sorry, x1 and y1. Okay, so again, 95% of the proof in mechanics of materials is stress times area. So what's area? This area and that area and that area. Okay, so if this one is original A norm, original cube, right? So you can have A norm as a blue shape, no problem. So you have your force here, sigma x A norm. Okay, and this is tau xy A norm. All right, so this is the force diagram. All right, next, this is theta. All right, so this is A norm. So A norm tangent for the yellow plant, this A norm tangent. All right, tangent, right? Remember the definition of the tangent. So here is tau xy A norm tangent theta, and here is sigma y A norm tangent theta. All right. Then here is A norm times secant theta. So you can get the oblique surface. All right. Oblique surface. It's called tau x1 y1 times A norm secant theta. And this is sigma xy A norm secant theta. Ooh, secant theta. Okay, so again, who is the unknown? Tau x1, y1, sigma x1. Okay, so we are going to make the pink highlight unknown to the left-hand side. And then, well, all we need to do is going to make it the same. Do the balance. Next step, balance. Yeah. So next page, I'm going to, sorry, I need to copy that, and I will plot into the next page. Okay, copy to the pass to the next page. All right. Okay, sorry, to save some time. Yeah, very nice. Okay. And then I'm going to highlight pink sigma x1. tau x1, y1 here. And the rest of that are all known. Okay, we know the value. Next, I'm going to quickly using here. This is okay, 2 green parallel to the new x1. Okay, and okay, there are four turns. Okay, green one and purple one. Purple one is going up along y direction. But here you need to be careful. Okay, in the green, everything is going to the negative x1. So everything is minus, 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 minus. But here, there are four purples. Four purples. So 2 of them along the positive y1. And the other 2 is negative y1. So you need to see positive, negative, negative, positive. All right. I believe you understand what I'm talking about. This is not difficult. So now, I believe you understand what I'm talking about. This is false equilibrium. Okay, 95% proof. Right? So you know what to do. You put all the green to the right and then divide by a naught second theta. And you put all the purple to the right and divide by a naught second theta. Again, you can obtain sigma xy, tau x1, y1. And then you can get the results in the next page. Okay? Awesome. Okay, so next page. We found that it's really similar to what we done in chapter 2, right? Very similar. Okay, so next page. After you've done that, you got the formula. Looks like this: sigma x1 equal to blah 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 blah, or tau x1 y1 blah 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 blah. Now, remember we talked about the double angle cosine sine. I don't know 背角公式 how to translate that. If you make the cosine square theta into something about cosine 2 theta, and you mention 2 sine theta cosine theta become something sine 2 theta, you will end up making everything here into the bottom form. Okay, so sigma x1 equal to the average of the sigma x plus sigma y, and minus them together divided by 2 times cosine 2 theta, and the shear times sine 2 theta. All right. And yeah, looks like that. Okay, I will prefer you memorize these three, these two. Why? Because this will relate it to more circle, more yuan. Okay, actually, these four equations are all equivalent. Okay, the same. They are the same. But I would prefer you remember this because this one is related to more circles, more. These more circles, I will guide you to do that, and you will find that this is actually the origin, starting point of the more circles, and it will be really interesting. So again, you got the formula. Now I will give you, you know sigma x1, tau x1, y1. How about sigma y1? Sigma y1, what is, how to do that? Actually, your theta is arbitrary number, right? So previously, your theta is theta. You are going to get sigma y1. So you got theta plus 90 degrees. So you can get sigma y1, okay? So your sigma y1 will be equal to sigma x plus sigma y divided by 2 and minus sigma x minus sigma y divided by 2 cosine theta, because cosine 2 theta, because when you substitute theta plus 90 degrees, your cosine 2 theta will reverse. It's sine tau xy sine 2 theta. Okay, so this is your sigma y. If you substitute theta plus 90 to the original sigma x1 formula, you will obtain sigma y1。这样听得懂哈？就是我们刚刚算的 sigma x1 的 sigma 的 stress 是这个式子。那其实我们 theta 没有告诉你要多少啊，所以我们只要把 theta 加90，我们就可以把主角面换成上面那个面。那等一下算出来的 sigma x1 就是我们现在的 sigma y1 OK， 那就算出来以后发现，其实 theta 加90度以后带入这个 cosine 2 theta 会让它 cosine 变负的，然后 sin 会变负的，就这样。OK， 那这就是 sigma y1。Okay, so when you obtain sigma y1, sigma x1, we can give you a new finding. Actually, sigma x1 plus sigma y1 equal to sigma x plus sigma y. So we call this stress invariant. What is invariant? Variant, which is 变来变去, changing, okay? Invariant is not changing. So no matter how your axis change, the stress invariance stay the same. So your sigma x1 plus sigma y1 always equal to sigma x plus sigma y, okay? Well, you learned this in chapter 2 as well. So now, some special example of plane stress. Special example. All right, here, next one. Example of plane stress when you only have simple axial force. So your sigma x not equal to 0, clearly, okay? But no force on the y, so sigma y equal to 0, no shear stress. How x1 or how xy equal to 0. So if you substitute all this into the formula we just obtained, we find that sigma x1 equal to this one. How x1 y1 equal to that one. Hey, don't you think you saw this in chapter 2? So actually, chapter 2 things is a special case in chapter 7. Okay. Or if you have pure shear, no more stress. So you will have sigma x1 equal to this, how x1, y1 equal to that. Actually equal to what you've seen in chapter 3. So basically, what I told you here is not new. Okay, it's not new. They actually kind of extension of chapter 2, chapter 3. Chapter 7 is a general case. Okay, general case. What is general? 更一般化的，更 不是 special case， 不是特例的，这个是适用于所有泛用型的。OK， very nice. So you are now ready to do this problem. So this is a problem. I will give you the problem. Okay, this and that. So when you see a stress element like this, you have 12 MPa as your sigma y, 46 MPa your sigma x, and 19 MPa for the shear. Of course, actually 19 MPa should be write down 4 times. Sorry, I just write down 3 times. I'm sorry. Okay, but you know that. And you see, this is minus 46. So you see this compression. Sigma y here, 12 is a positive. This is,错了. So this is tension. And tau xy is minus 46. Okay, so minus 19. Minus 19 means that tau xy minus 19. How to make it minus? You have a positive x surface. You have minus direction in y, so you will have minus 19. Okay? Typically, we will use the right-hand side as the main focus, plan of focus, 主角面. We typically use the right-hand side. Okay? So you can use that and fix the direction of the shear. And it wants us to get the theta minus 15 degree for new axis. So previously you get the x in this direction, but now you are going to have 15 minus 15. See, minus 15. So you minus 15 degree. So you see here, I just write down 15. Okay, it's because the minus you have designed determine the direction. Okay, clockwise means negative direction, and here of course. So this is y1. Okay, so now actually it is asking. 好像也没有比较好。那我想想看哦。Okay, so you are going to find the stress on this orientation. Okay. Right. So how to do that? First one, sigma x1. All you need to do is substitute. No. All you need to do is substitute the formula. Average plus sigma x minus sigma y divided by 2 and cosine 2 theta plus tau xy sine 2 theta. Okay, and equal to, okay, careful. Minus 46 plus 12 divided by 2 is minus 17. So you need to be careful. The plus sign and minus sign still be, important. You need to take into the consideration. And then minus 46 minus 12 divided by 2. So it will be even greater. Okay? N times 0.860. So this is cosine 2 theta plus minus 19 because tau xy is 19 minus 19. Sine 2 theta is minus 0.5. So you see they are all relevant. Okay, the sign does matter. Okay. 符号是很重要的哦，不要忘记它了。Okay, so you got minus 32.6. Okay, your 6 sigma x1 is minus, which means that it is compression. Okay, compression. And the opposite side has compression as well because you need to balance at force. Okay. Now, tau x1, y1. Substitute minus sigma y divided by 2 sine 2 theta plus tau xy cosine 2 theta. So you get minus 26 minus 0.5 plus minus 16 0.860 equal to minus 31.0 m. Okay, again, tau x1 y1 is minus. Okay, where's tau x1 y1? You see, we are focusing on positive x1 direction, and now we are going to have negative shear, so it must go through minus y1 direction. All right, so here is not minus. All right, so sorry, I forgot to write the sigma x. So sigma x is 32.6 megapascal, and you see that I don't have minus 32.6. I just write down 32.6 because we know the direction. Okay, and shear is 31 megapascal. All right, and the opposite side also have 32.6 6 megapascal. And now you know shear is come in pairs. Okay, so the opposite side will have a upper balance shear and 31 megapascal. Okay, and come in pair, right? So up R and bottom part. Okay, they are all 31 megapascal. Are they done? Are we done? No, because we haven't found the sigma y1 yet. How to determine sigma y1 yet? Sigma x1 plus invariant, right? Sigma x plus sigma y1 equal to sigma x plus sigma y. So you have sigma y1 equal to minus 1.4 m pa. So it is, again, this is compression. So compression for sigma y1 and the opposite side. And this is 1.4 m pa. 1.4 m pa. That's it. Very easy. Okay. Now, this is an easy question, the easy example, but I would like to go back home to check. Okay. If you check theta equal to minus 15 degree plus 90 degree. Okay, and what will it be? If you check theta equal to minus 15 degree plus 90 degree, you end up determining sigma y1. All right, so you will get, suppose you will get 1.4 MPa. Okay, so you will get you will obtain sigma, well, it should be, you should get the new sigma 1, and you will get new x1 y1. Okay, but this x1 y1 is not the one I draw here. Actually, this sigma x1 y1 actually will become this. Okay, the main focus will be in the y1. Okay, so you need to go back home, check that. And very, very important thing is that the tau x1 y1 should be really careful. Okay, why? Anyone wants the bonus? Anyone want a bonus here? Can you predict if you check theta equal to minus 15 degree plus 90 degree, what is the sign, positive or negative, for tau x1, new tau x1 y1 for this pink area? Anyone? Anyone? If you substitute this theta into this equation, what will this new tau x1 y1 in this pink, the value will be positive or negative? Anyone? About 50% chance. Okay, please. Positive. Very nice. Why? Why? Yeah, yeah. Positive direction, right? Very nice. Wow, you are really, your concept is connected. 就是融会贯通啊 how to use English. Okay, very nice. They will be positive. Yeah, please let me know your number. 613 double 9. Wow, you see, close to this end of semester. Now everyone will say double O. See, that's really, this is improvement, Previously we just said 0, 0. And then in the middle of the semester, we'll say OO. And now double O is even better. Wow. Okay, so I can see your improvement. Very nice. Okay, yes, this will be positive because your focus plan has your new x1, new y1 here. So actually, when you determine this direction, it should be positive, but it will be different from this minus sign because your focus is different, your coordinates different. Okay, so what she says, totally correct. Totally correct. Okay, good, very nice. So suppose I should finish here, but this time I remember I can go to the 10 o'clock. All right, so we still have 10 minutes. Next one, I will tell you the principal stress. As you know, the logic flow is really similar to chapter 2 and chapter 3. After we done the formula, we found that actually it has sine and cosine. So which means that we have maxima or minima. Now, principal stress is actually assessing the maxima or minima in this form. So maxima or minima value, how to do that? We just do the differentiation and equal to 0. So this is differentiation equal to 0. So what will it be? the value is the solution is tangent to theta equal to 2 tau x y divided by sigma x minus sigma y. Okay. So now I'm going to say this is really important. After you do the differentiation equal to 0, your tangent to theta need to be equal to this. And then it will make the differentiation become 0. Okay? So actually this theta is not changing. It is one specific value. So you shouldn't write down theta anymore. This is a solution. So suppose you will give it a name called theta p. 听懂我在讲什么吗？就是我们在做微分以后等于0，它的解叫做 tangent 2 theta equal to 这个东西。那这是什么？这表示说你的 tangent 2 theta 要等于这个值哦，这个值会让这上面这个东西有极值，所以说这个 theta 不再是变数了，它是一个真实的数字，它是有解的，解出来要等于这个值哦，它才会让它变大、最大或最小值，应该说最大值或最大正值或最大负值吧，哈。那所以这边我们要给它一个值，叫做西塔 p， 我不能写西塔，因为西塔看起来好像就是它会变来变去，不对哦。现在西塔已经是定值了，西塔 p。Okay, so if you can get this, tangent to theta p will equal to this, and the theta p will make this sigma x1 become the maxima or minima. Okay, and now further to make this formulation more close to what we learned in the formula, actually we prefer to write it down like this: tau xy divided by sigma x minus sigma y divided by 2. Okay, we prefer like this because it looks similar here, right? Tau xy, kind of similar, right? So now tangent to theta p, if the tangent to theta p equal to this value, don't forget tau xy, sigma x, sigma y, they are all known. You know the value. Okay, so you can get this value and you determine theta p. So this theta p will make sigma x1 maxima or minima. All right, 听得懂哈？就是这三个值 tau xy sigma x sigma y 都是你知道的值，都是题目会给你。OK， 你有这些值了，你就可以反算出西塔 p 该是多少。这西塔 p 带入这里面，就会得到 sigma x1 最大的值是多少。也就是说，这个西塔 p 其实就是你转到哪个方向的时候，你的 sigma x 会是最大的 ，sigma x1 是最大的。Okay, so if you can understand this, next page is kind of difficult. I would like you to listen carefully. All right. So now, you know tangent to theta p looks like this, right? This is obtained from the previous page. Okay. Now, we want to get cosine to theta p and sine to theta p to substitute to this cosine to theta, sine to theta, and obtain the sigma x1 maxima or minima, right? So we know tangent to theta p. Can we get cosine to theta p or sine to theta p? Yes, we could. All we need to do is plot a 90-degree triangle. And we know that tangent to theta p equal to this, Okay, so tangent, right? Tangent. Okay, so you see, we plot a triangle with the 90 degree. This is this one, sigma x minus sigma y divided by 2. And tau xy put here. So this triangle tangent will become tangent to theta p. You know that, right? So we can use the formula. 哇，糟糕，毕氏定理的英文我不会讲。毕氏定理，哎，知道英文是什么？毕氏定理 ？I don't know 。So, square plus square equal to this, and do the square root. Okay, so you get r equal to this square plus this square, and do the square root. You got r. So the oblique edge length, you can obtain that, right? We call this r. We call this r. So your cosine to theta p will be equal to this, right? And your sine theta p equal to that. Hey, do you know what I'm drawing? You know, right? Okay, everyone know what I'm drawing, right? That's how I learn, how I memorize cosine and sine in my senior high school. I believe you, right? Okay. So your cosine to theta p is a r the sigma x minus sigma y divided by 2 over r, and your sine tau xy over r. Okay, so you substitute this. Ugly. Hey. Okay, and you can obtain sigma x1. All right, so easy. This is a solution one. 你看懂我在干嘛吧？哈，我们找到了 tangent to theta p， 但是我们其实不是想要知道 tangent to theta p 啊，我们想要知道的是 cosine to theta p 跟 sin to theta p， 怎么办？没有关系，我们用回归最传统的方式，我们就画一个直角三角形，然后底边就是我们这个高就是这个，我们的斜边就用毕氏定理算出来，然后我们就可以算出它的 cosine to theta p 跟 sin to theta p， 代入就可以得到 sigma x1。OK。得到第一个解。So I just said I just mentioned one solution, which means that we have second solution. Also, we also need to know we have the second solution. Why? Because if you know that tangent, if you plot tangent x in the figure, your tangent x looks like this, right? L, 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 and infinity go infinity, right? But your rotation is from 0 to 2 pi. So your solution must be exceed between 0 and 2 pi, right? So actually you have solution here, okay? And you must write down as you only have one theta p. So your theta p, I mean, you will get the value by swiping one direction, and you will obtain two solution. Okay, so your solution one, suppose one of it, and you have the other. Okay, so this is a smaller angle form, so you obtain this, and you will have another solution in between 0 to 2 pi. So you actually need to rotate this 180 degree to obtain that the other solution. All right, sorry I don't have time, but you got my idea. So please, this page is a little bit difficult. Please think when you go back home. Thank you. So I will see you next week. If you have any questions, just come here. Thank you. 哦，有点难哈，就是之前的那个啦，广义三角函数啦。来，请问。OK， 你的意思是说，你画出来这个东西这样子的时候，是，嘿，
它冲出来会是正的，因为你知道从这边。
好，你说的非常好，因为你这样子往下，你这个方向是对的，对不对？已经算出来它是对的。好，那可是你看哦，你做出来这个，你要切的时候，我直接画这边。好，谢谢。这样对不对？你这个是这样子，对不对？但你要开始画这个值的时候，你是要切这里的，你要留这里的，那你算出来的 moment 会是这样吗？要去抵消它。
这题是，我觉得它是要说
留右边啊，留。看一下你的 MB 这边的我这边是我的 MB 对不对？我的 MB 是这是我算出来的方向，这个是对的吗？是这样嘛，对不对？哈，所以说它是在这里嘛。那表示说，看一下，哎，对啊，所以它是在右边啊，所以它是往下，没错啊，它在右边呢、啊。所以怎么讲？我看一下哦，如果你这个东西应该是要计算，我看一下哦。好，原来是这个。如果是这一个题的话，这一题的话，你说到最后的时候，我这边是往上的，对不对？好，
哎，不对，这边最后算出来是
负的，所以是往下，所以是往下。好，那这表示说这边在你快要到底之前，我切了。你如果留左边可以，那但是我如果切我留右边的话，它会是这样，它会是这样。那你告诉我这边的是这样子咯。所以说你不要看右边的时候，就是你从左边推进过来的时候，它会一直都是往下的、啊。对，那推到最极限的时候，这个就会跟这个重合啊，所以它就是负担。这样可以吗？想一下，对，就当你不懂它的方向的时候，你就回到原始，切开看左边看右边，然后我们要画的那个图都会是留左边剩下这样。那我先把这个结束掉。Stop recording.